Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, it's my great pleasure to have Tim Wood visiting us from Imperial College, London today. Tim has been working with Sophia Drossopoulou for the last couple of years on the idea of program equivalence and theorem provers, and that's something of interest to us. And so I think he's going to present two talks today. First one he just presented at a workshop at Splash, and the other one more of a work in progress. So yeah, Tim, welcome.
Great. Thank you. It's nice to be here. Yeah, so I'm going to talk about two pieces of work. The first one is a joint piece of work with my supervisor, Sophia Drossopoulou. So the context is we're interested in program maintenance, where programmers have to take an existing piece of software, potentially a large piece of software, and make some kind of modification to it, change its behaviour, add a new feature, fix a bug, something like that. And when they do that, they usually want to somehow preserve most of the behaviour of the existing program. What they don't want to do is unintentionally break some existing part of it. But usually they don't want to, or there don't exist specifications for the entire program, maybe not tests or very good tests, and they don't really want to have to read the whole program first. Certainly don't want to have to understand the whole program before they can change it. So the two questions that we're trying to address here are what exactly does it mean to preserve most of the behaviour of a program, and have we got some way of checking whether or not they've done that? So what I'm going to do in this talk is try to propose some precise criteria for this kind of partial preservation of behaviour, and which is that only some objects should be affected by the change, and the rest of the objects should continue to behave in the way they did previously. And we're going to ask the programmer to tell us what those objects are. So they're going to provide us with some expression which says this change was intended to impact these objects, and if it impacts any others, then it's done something that I didn't want it to do. Sorry, I should have changed the slide earlier. And then we need some way to check this. Now we're developing a tool which does test generation to try and produce tests that falsify this condition. I'm not really going to talk about the tool. I'm just going to focus more on the formal side of it. What we wanted to achieve was that we didn't need to track all of the unaffected objects during the whole of the program execution in order to be able to check these conditions, because the program's been very big and we don't want to generate tests that have to explore the entire program in order to explore the bit that we've changed. So we're going to propose this sufficient condition for our behavioural equivalence criteria, that says that if the trace of method calls between the bit of the program that we wanted to impact and the bit that we didn't are preserved in some way between the two executions, then we know that the impact is contained within those affected objects. We did a proof, machine check proof using Dafny from Microsoft, which maybe I'll talk a little bit about depending on the time. So this is a kind of small example program that gets a list of students from somewhere, from a database, and via some calls eventually tries to award a prize to the top 3 students in the list. And, oh, wrong way. I'll go back. One of the things that it does is it prints out the names of all of the students that it considered when deciding who to award the prize to. But it prints it out in whatever order the list happens to be, and a developer decides to come along and change it so that it prints the students in name order. So what we ask the developers to do is tell us to allege that some of these objects are affected, and then we assume that we take that to mean that the developer did not intend to affect any other objects. So here we expect the object that's doing the I/O to be affected, the logger to be affected, and the objects in this list to be affected, because we're going to try and sort them. So we're going to have to query them. We're going to have to query the list. We're going to have to query the students, which means calling additional methods on them.
When you say object, do you refer to program expressions, or do you refer to the entire class?
Right. So actually, what we do in the tool, which I'm not going to talk about, but the programmer can give us an arbitrary, a side effect-free Java expression that we run when objects are constructed to decide whether or not they should be affected. So they can write anything they want over the whole state of the program at that time. So it can be the class of the object. It can be, we know which line we were executing. We know something about the context, at least, some over approximation of the context. So they could say all of the students' objects constructed inside the database, or they could say the object on line 20, or it's fairly arbitrary what they can write, but there's a trade-off between that and the performance of the analysis. So if they write something that's very difficult to calculate, it's going to take a long time to run. Because we're going to explore lots of paths through the program, and we have to run it a lot of times.
When you said test generation, your goal is to generate falsifying runs that falsifies the allegedly affected.
Right, exactly. So we're trying to find some input for the program that produces. If we run both versions of the program, produces at some point program states that we can't match together. But I'll say precisely what I mean by match together shortly. So here, this program has a bug. This sort has a side effect on the list. So by the time we get to here, this object is going to execute differently. It's going to get different students and give them the prizes. Alphabetically, first students will get the prizes, which is good for some people, not for me. So I guess the motivation for using this criterion is that it doesn't require the programmer to say anything about the part of the program that they aren't impacting. The idea is that they only have to talk about the objects that they intended to do something to. And hopefully they can not even read the rest of the program, and we're going to tell them if it was safe to do that or not. So what do I mean by have the states correspond? Well, we're going to say that they correspond when the stack and the heap have the same shape if we throw away all of the affected objects. So this is stack and the heap. This is from version 1, this is from version 2. And here this one has this additional pointer. This is a different program, by the way. This is actually a program that puts things in and out of a list. The stack and the heap of the other example is too big to draw. So these don't correspond if we consider all of the objects, but what we do is we delete the unaffected parts, and now they do correspond. They have exactly the same shape. So what we didn't want to do was have to precisely execute both versions of the program, and at every pair of states try and decide if they correspond or not. So what we're going to do is only compare the method calls between these allegedly affected and unaffected objects. So this is an execution of version 1, this is an execution of version 2, and these are all different states. I drew them all the same. It's really subtle, isn't it? I meant to fix that. So we only have to consider some of the states. So here, this one, this one, this one, this one, this one, this one, which are where method calls happen. Method calls or returns happen between the affected and unaffected objects. And actually, we only need to consider the topmost stack frame of each of those states, which will have the method parameters or the return value in it. I guess the nice thing is that this sort of abstracts the difference in the number of execution steps which can occur in the affected part. So we don't have to search to find out which states to compare. We just pick these precise points in the execution. So we end up having to do something like this. I guess the intuition is that the code of the unaffected objects and the values in the method calls uniquely determine the way that the unaffected objects will execute. So this is what we do, the traces. So this is the trace of calls and returns between the unaffected and affected objects. These are the values, which are pointers into the heap. These are addresses, although we can deal with primitives and things as well. I haven't shown any here. And this is the trace from an execution of version 2. And we can see that the trace has the same aliasing structure. So everywhere there's a 10 in this trace, for example, there's a 3 in this trace. And that's what we need to check. It's quite straightforward to do. Just read.
The stack frames?
No, it's a trace of method calls and returns. So whenever, we have, for example, the call. This is a constructor call, and then a return, and then sometime later we add something into the list, and then there's a return, and then sometime after that we add something else, there's a return. Remove something, return, remove something. So it's like, I guess you can think of it as the protocol between the affected and the unaffected objects. We arbitrarily partition the program and then try to examine the protocol that's observed between the two parts, and then see if it's preserved between the two versions. And if this contains all of the information that flows between those two halves of the program, then we can say something about the equivalence of the bit where the code is the same. Did that make sense?
these numbers in particular, should we think of them as the values of the pointers themselves?
Yeah, they're the values of the pointers.
Mm-hmm. Okay.
So, I mean, they can be different between different versions of. I mean, they can be different between different runs of the same version, just due to address allocation, and they're certainly different between different runs of the same, different runs of different versions, because the modified version is free to allocate extra objects, not allocate stuff, do whatever it wants. I guess the point is that so in Java generally you can, ignoring some slight problems, but which you can detect and deal with, but the only thing you can tell about an object that you've been given a reference to without sending it a method is whether or not you've got the same object at 2 points in the execution or different objects. So it's sufficient to just check whether or not when you talk to another object it's giving you back the same reference or a different one. And if in all the places in the first version where it gave you the same reference it does in the second version, then you can't observe any further anything else about what's happening. There's some things to do with hash codes and reflection, which occur in Java, and in various other languages there's ways to actually get hold of the real values, unfortunately. But you can easily check whether or not a program's doing that, and then tell the program that it's happened. So this is an example of one which is not the same. So here there's a 4 here and there's a 1 here, but here there's a 2 and a 4.
So in general you also look at the graph of the heap and then do the isomorphism?
No.
No?
So what
Just looking at the roots?
No, we literally just look at these numbers. So what we don't look at the heap at all. So what I do in what the tool actually does is it maintains 2 separate address spaces based on whether or not the objects are affected or unaffected, which makes detecting the traces very easy. Whenever you have a call between an object in one address space and the other, you know you've got the trace, and then it keeps track of the order that it saw the objects in. So when it sees this one, it tags it with 1, and then this one it tags with 2, and then it sees a new one, it tags with 3, just with the counter. It does the same thing in this one, and then if the traces are equal. So it's very, very cheap to check. The only slight, the thing that makes it less cheap is that if you've got, I'm not sure if I should get into this, but if you've got primitives in here and you try and do it slightly more abstractly, which we do with the symbolic executor, you have to check if the primitives were calculated the same way, or if equivalent values have been calculated for the primitives. But certainly for the object graph, it's extremely cheap to check. The only problem is obviously having to produce these traces.
So where does the affected and unaffected set of objects show up in this picture? Are you taking advantage of that? The
yes.
Specification?
So the only things that appear in the trace are calls where either the caller was affected and the callee was unaffected, or vice versa, including constructor calls and returns. So we're trying to capture the flow of information between the two parts.
Could you turn the whole thing into an inference problem where instead of letting the programmer specify these sets, trying to infer them and present it to people, sort of just doing this iteratively? Or would it be too expensive?
Yeah, it's something we considered. I think that what you could probably do is take some. There's probably other things you could do as well. But something that occurred to us was that you could take the test suite and run it, and then try to guess some partition based on that, and then do this to try and explore whether or not that was reasonable partition, or but you do and you can give some kind of meaning to that partition by looking at whether there's IO operations occur within the with which IO operations occur within the affected part, to try and give it some meaning to the programmer, because otherwise if you just come up with some, there is always some partition, so you need to sort of then somehow give the programmer some help about whether or not this was the one they wanted or not, and asking them to specify it is a very firm way of doing that. They have to think about it for themselves. But
I suppose you could you could try to find a minimal partition, right? I mean, where say you minimize the number of affected.
Yeah. Yeah. Yeah, and I think it could be useful to try and do that. And if you can generate a big set of traces somehow, it's very cheap to check, so you can probably try and brute force it in some way. Yeah, cool. Yeah, so there's a bunch of other things that you have to check that you're not doing. Very few programming languages actually abstract the addresses completely, it seems. So I don't know. So I'll try and talk about this quickly, and we can talk about it more if people want to. I've got some extra slides with more details on if we wanted to get into that. Or so yeah, I gave this talk at a workshop, and I guess I was doing a bit of a Dafny advert, so it's not very specific. But so what we do is we write a function that actually executes the operational semantics of the language that we're interested in. You can run this. This here we have the instructions, and then you can just do a case split, calculate the next state of the program. So instructions, you have this non-ghost method. And then the lemmas are written as procedures, so here we're going to try and do a proof by induction, which means doing this recursive call back to the lemma. So it's this ghost imperative code, but we're going to use it to prove this declarative theorem. So you read it as the parameters is universally quantified and the return values is existentially quantified. So we're going to say for all of the parameters there exists some return values such that the precondition implies the postcondition. So here this is our trace equivalence. So we're going to say if we start with these two states that are trace equivalents, then we're going to end up in equivalent states always, and some other stuff as well, but that's the gist of it. And then you can just write normal imperative code. So this is the base case of the induction, which Dafny is able to prove automatically. That's the inductive step. I haven't put any of the detail on there, but I have some extra slides if we want to talk about it more.
I'm sorry, what does the theorem roughly say?
So the theorem here says that, so this says S1 executes to S3 by trace ls1. So this is the traces like I showed previously. And we know that executing S1 and executing from S1 and executing from S2 are trace equivalent. So we carry the version of the code around in the state. So this says that by some method, we've established that they're trace equivalent, so just by inspecting the traces. Then it ensures that there exists some trace from S2 to reach a state S4, such that the traces are equivalent, which is comes basically for free from that. But this is the main one, which is that whatever's at the end of the trace, the states at the end of the trace will be compatible in the way that I described. So if you throw away the affected parts, they'll be equivalent. So this essentially says there is an isomorphism that relates these states. And then we argue inductively by looking at the first step in the execution, and then the rest of the execution, and so on. But it's big. It's like 6,000 lines of Dafny, something like that. So it's a bit.
The reason you didn't quantify S4 is because you need it when you return. And you could have written the ensures as there exists an S4.
Oh right, yeah. Something uses it here. So then there's some more. So there's a determinism argument that goes after this in the proof. So we have to say that there is only one of these, essentially. We made that argument.
You could have treated the AL in line 5 in the same way. So LS2 and S4 are out parameters, which, as Shuvendu said, I mean, it could have been, you can think of it as that there exists an LS2 and S4, but you're just going to give them and return them. But you could have done the same thing for AL.
Yeah, the only reason I don't is because didn't have to use this afterwards.
Yeah.
So yeah, they mean exactly the same thing. Yeah, but I would have had to assign it here and then not use it. So
Right.
yeah. But it's very useful. I mean, otherwise you would have to call this and then do like an assign such that and so on to get these back again. But here you just write it all together, and it's a lot neater, right? Okay.
And the state S does it have the entire stack, or is it just
the states? So the states here are. Can I come back to that? Well, there's another diagram later, and I'll explain it in the it's not about that, but it'll make it clearer why I'm going to give the answer that I do. So it's a reasonably big proof, and some of the predicates are quite large. So the operational semantics predicate is reasonably function is reasonably big, and we have these predicates over the whole state saying what doesn't change for every kind of instruction that you can execute. They're quite big as well, and we use those when I first started doing this, we used those together in quite a few of the theorems, and I was so when the proof is correct and complete, it goes through quite quickly. But when you're trying to write it, a lot of the time you end up with timeouts because the SMT solver's sitting there trying to prove something that either is not provable or you haven't given enough detail for it to prove. So a lot of what the approach that we took to doing it was related to not related to how well it's going to perform when it's all complete and working, but how well it's going to perform when you're editing it and making changes to it and trying to get it to work. And if you have a lot of I guess axioms or lots of different ways that that Z3 can proceed to then with searching for the proof, but there is not a proof available, then it can take a long time for Z3 to come to the conclusion that there is not a proof available, I guess. So you end up with a lot of timeouts. So what we did was split the proof up into a number of modules where we... So I should give some background. So you can have abstract modules in Dafny where you can define lemmas with no bodies, which essentially act as axioms within those modules. You can have abstract data types, so types where you just give them a name but you don't give any concrete implementation. And then you can use this process of refinement where you say that this concrete module refines this abstract module, and here you have to give bodies for everything. You have to give concrete types for all of the abstract types. But what it allows is that you can have some proof here of our main theorem that depends on these abstract modules, where the final concrete implementations are not exposed to this theorem. So it doesn't have when you're working on it, it doesn't have the opportunity to go running off trying to prove things with these much bigger concrete definitions. It has what it has there, and it can exhaust them quite quickly normally. This is my understanding of what's happening anyway. Maybe Ruslan can contradict me at some point. But so we split this this proof up in this way. I guess the kind of nice side effect of that is that what we ended up with is something where the concrete semantics of the language are not depended on by almost the whole of the rest of the proof. So you can switch different representations and slightly different semantics in here and reuse the rest of these pieces. And if you're willing to change these bits, then you can substitute very different languages into the proof and still reuse these bits. So this kind of performance, trying to strive towards performance, led us to produce this much more modular and potentially reusable thing, which is kind of cool. So to answer your earlier question, the states in that the lemma that I showed you previously is in here. So the states are quite abstract. They don't actually have anything in them like objects or heaps or anything. They don't have anything in them actually. And then we provide some refinement that talks about heaps and stacks, but actually that lemma will apply to anything for which you can provide this refinement. And I haven't tried it, but a language that didn't have a stack and an object, that theorem depends really only on this notion of labeled transition systems. So if you can provide a labeled transition system and a mapping and an isomorphism between two labeled transition systems for your language that is preserved at each step in the execution, then you can reuse the theorem. So not necessarily even objects, if you're imaginative enough, which I'm not so far, but you could try it with a completely different kind of language. So that's the first talk finished. I don't know, should I just jump straight into the next one? Yeah. So the next part is kind of related in some ways. Again, we're looking at a program equivalence and isomorphisms. This is joint work with myself, Shuvendu's here, and again Sophia. But here we're going to look at kind of program verification-based approach. This work in progress, so some parts of it are not quite complete, but hopefully maybe some people have some things to say about it here, so that's good. So why is it useful? Kind of similar to what I said previously. You know, you've changed the program in some way. You want to check that you've only changed the bit of it that you wanted to change. And maybe program equivalence is useful in some other places as well. People use it for trying to check that compilers are correct and compiler optimizations are correct, for example. So one thing that is kind of difficult to do with the current state of the art is deal with modifications to programs that affect the way that memory is allocated. So if you reorder allocations, or you have extra allocations in one program, or remove or less allocations in one program, particularly it's difficult if you allow loops or recursion that can make unbounded extra allocations or different allocations. So that's what we're going to try and address here. So first of all, what does it mean? What's typically done to compare programs for equivalence? So here's two programs that are more or less the same, except the order of the allocations has been changed between the two versions. So if we use a program verification approach, we would equate the initial state. So we say that X has the same value on entry. Then we make some non-deterministic memory allocation, and here we get these two addresses, and here we get these two addresses. Now we need to establish, in order to establish these procedures are equivalent, we need to establish that these calls are going to do the same thing. But they're being called with different values, so that's difficult. We don't know whether or not those procedures are going to be equivalent. So a kind of typical thing that people do here is try to just assume that the allocation is going to be deterministic, that we're going to have some pool of objects available, and we're just going to allocate them in the order that they're asked for. So we get 1, 2, 3 here and 1, 2, 3 here. But because these allocation orders have changed, we're going to call F here with 2 and 3, and F here with 3 and 2. So again, it's difficult to modularly this idea that we can then equate the initial states of the procedures is we can't make that assumption here because the initial states are not the same. There are some other approaches that people take, particularly modeling the heap graph explicitly up to some bound and trying to look for isomorphisms. But you can't really do that if you have these unbounded updates by called procedures. So what we do instead is we require, prior to the call, we require no, start again. So what we're going to do is going to say that that the programs are equivalent if there is there's some mapping between the addresses, some isomorphism between the objects that have been allocated that preserves the structure of the states of the programs. So so if you start at the stack variable X, for example, then you reach 1 and 1 there, and 1 are mapped here. I hope everyone's following that. But again, we have the same issue with calls. Sorry, I haven't given this presentation before, and I've kind of missed a step. Okay, I might have to draw it. Oh. So what we're trying to do is prove that in order to check whether two programs are equivalent for all isomorphic initial states, it's sufficient to check that they're equivalent from all equal initial states. So we say that if we have some program P and some program P prime, then they're equivalent if and only if for all initial states which are isomorphic, then running P on is isomorphic to running P prime on the other one. So that's what we're trying to establish, that running the two versions of programs from isomorphic initial states, we reach isomorphic final states. And what we are currently in the process of proving, which we believe to be true, is that if you run the program from the same initial state, if when you run the program from the same initial state, you reach isomorphic final states. So if you can establish this, then so it's sufficient to check the program from all equal initial states to prove that it's equivalent for all isomorphic initial states. What that allows us to do is, just at some arbitrary place in the execution of these two programs, where we've established that the states are isomorphic, is to swap them for equal. So that's what we do here. We first of all do it for this call. So we say, well, we've established that they're isomorphic here, so we can use our rule that these things are going to behave the same from equal states, just by swapping isomorphic for equal. And then we're going to do it now. F is going to run, it's going to return us some isomorphic state from the initial states, from the same initial states. And we're going to swap it again to equal states after it returns.
So I think abstractly, if I understand, you're saying that the execution cannot distinguish between isomorphic states and equal states, right? Something like that.
That is,
in terms of proving isomorphism.
yeah, that's the critical thing. That's the critical feature that allows you to do this.
I guess it makes certain assumptions about what you're allowed to do in the program, right?
You have to have you have to have a program that doesn't distinguish the values. So either a language that doesn't, or a program that doesn't use features that where it will distinguish the values. Similar to what I was saying in the previous presentation, actually. And yeah, so So it turns out that if you do this and you use this kind of very abstract map encoding for heaps, that something like the Boogie intermediate program verify can do this check for us. So this is, with some slightly invented syntax, is what we do. So this is similar to the kind of previous work that Shuvendu's done with mutual summaries. So this is the first procedure. We put the body of it here. And this is the other procedure. I don't know why I've got pre-prime before P, but I have. Yeah, sorry about that. That should be P and that should be P prime, but we'll have to live with it. Then we start again from the same initial state, run it again, and then we're going to check that the final state's isomorphic.
Just for the motivation, so is the idea to now combine this with the first idea of the first part of your talk, where you're saying that you only look at functions at the boundary of the affected or unaffected.
Right. So the question is going to be what happens if P calls another procedure.
Yeah, for example.
Yeah, but we're not talking about object-oriented programs here, or well, they could be, but this is just any kind of program that is dealing with dynamically allocated memory. But we're not going to make a distinction between affected and unaffected. We're looking for procedures which are equivalent. If it won't deal with any procedures, well, at least what I present here won't deal with procedures that are not equivalent in any way. Although there are extensions that you can do to deal with procedures that are only equivalent over like parts of the input state.
We did some work in compiler verification, and there we had different offsets show up from different runs, and so you can think of this making SIMDIF more complete for programs like that.
It allows you to do some things like allocate some heap temporary space within a procedure, and as long as you throw it away by the end of the procedure, we can show that the procedures are equivalent, which is very difficult to do with the current systems. So one of the challenges is the context of the call. You can have some arbitrarily big, uncomplicated calling context. So here, for example, we have two procedures which are not equivalent. Yeah, right. So they both allocate two new objects. This one then makes 2 unreachable from X, whereas this one points it here, it points it there and then makes it unreachable from X. This one points it here and then makes it unreachable from X. And if you consider this locally, so just from the context of the callee, then this is isomorphic. So you have this graph and you have this reachable part of the graph. But actually, these in any or in some bigger context, these two procedure executions are not isomorphic. So we have to have some way of saying, talking about global isomorphism of the heaps at the end of the procedures, even though some parts of the heap may no longer be meaningful. You can't just talk about paths from the procedure parameters, for example. So what we do is we require the isomorphism that we end up with to extend the initial isomorphism. You're not allowed to produce some incompatible isomorphism just in case there's some more calling context that can distinguish the two isomorphisms that you produce. And because we always start from the same initial states, the isomorphism that we extend is the identity isomorphism. So essentially say you must construct an isomorphism which is the identity for all previously allocated objects and is free for any newly allocated objects. I hope that makes sense. I can draw a diagram again if that. So, as you said, if you have a procedure that that calls some function inside it, some other procedure inside it, you have to have some way of using this this fact about the equivalence of these procedures in Boogie. So this is how we do it. We call them F and G. So we have this this mutual summary of the two procedures. So we give the procedures F and G this free post condition, which is a post condition that you just get to assume after a call to either of these procedures, but it's not checked. So Boogie doesn't check it for the body of these procedures. And this summarizes the pre-state of the procedure call and the post-state. And we have to pass the pre-state as ghost state here. And then we have this axiom which is mutually summarizes these two procedures. So this is the summary for a call to F, this is a summary for a call to G. And if we can establish that the states are isomorphic before the call, then we get that that they're the same after the call. And this way we don't have to do any further work to kind of match up which procedure calls match with each other. Boogie's going to search and try and match them up for us. So I guess I'm just going to talk a bit about the kind of difficulties with the Boogie encoding and bits where I guess we're not entirely satisfied with what we've got. The first thing is it's quite difficult to use this idea of there exists a mapping between two heaps as your definition for isomorphism, because you have to somehow give Boogie something it can instantiate that existential with, and we don't have it. So what we do instead is try to universally quantify everything. So we quantify over paths from previously allocated objects and from the stack frames, and that works. The other issue is that it's very difficult to give this notion of unbounded reachability to an SMT solver. At least I don't know how to do it. But it turns out that you don't actually require an unbounded reachability predicate to deal with unbounded reachability, because although recursive calls can make unbounded updates, what we do is we change loops into tail recursion, and then each procedure call itself can only make a bounded update. So we only ever have to check isomorphism for some bounded amount of updates done within the statements of a particular procedure. but some nicer formulation of reachability would be very helpful. Yeah, and I guess the other thing that helps us is there's always exactly 1 or 0 isomorphisms. There's never many isomorphisms that we consider. So I've got some more slides on the actual Boogie encoding. They're kind of intricate, so we can go through them if people are interested, or we can stop here. So I'll leave it up to you.
Nice slide to
Yeah, well, it gets more complicated. Or if anyone has any questions about what I previously said, because it was maybe not the best presentation of it ever.
I could do the question, but I could also wait until the end. I mean, you're writing proofs and encodings essentially in Boogie, and you also, wrote lots of proofs and formalization in Dafny. In both cases, you're dealing with the same engine below. Boogie and Z3. Do you find a difference in the two? For example, if you were able to encode this in Dafny instead, if that would have been useful, would you have preferred that? Or for the Dafny encoding that you did of your first system, would you have preferred to have done that in Boogie?
So Boogie feels a lot like programming the SMT solver. You, in order to use it, had to read and learn a lot about what the SMT solver is actually trying to do underneath, how it's going to try and search the axioms, how it's going to try and build the proof tree. So the first several attempts that I had at doing this in Boogie were not very good. I guess the critical thing comes down to understanding how the triggers cause the matching loop to work. But I think that is very important here, because we're trying to talk about these unbounded modifications, and there isn't a decision procedure available. So you have to compromise in some places, and how you write the trigger expressions and construct the predicates is, I guess, how you tell Boogie what compromise you want. Whereas in Dafny, it felt much more like writing a program and doing kind of logic proofs on a program, and most of the time did not have to think very much about what the SMT solver was going to do. So it definitely feels very different, I guess, because Dafny has a carefully crafted set of trigger expressions that it's already got in its encoding. And I learned quite a lot about Boogie actually from going and reading how Dafny was encoding the programs. But I'm not sure how to bridge that. So here, where I feel that I need a lot of control over what I'm asking the theorem prover to do, and I might be mistaken, but it seems to be useful to be able to do that. And I'm not sure how I would achieve that to the same degree in Dafny.
Any more questions? thank Tim.